Chapter 1.4.1.1 Pod Lifecycle. Pods go through a defined life cycle, starting in the pending phase, moving to running if its containers start successfully, and then either succeeded or failed, depending on container status. They are considered ephemeral entities, created with a UID and scheduled on nodes until they are terminated or deleted. If a node dies, pods running on it are marked for deletion after a timeout period by the control plane. Pod lifetime. The text discusses how Kubernetes handles pods during runtime, focusing on fault recovery and scheduling. When a pod is running, the kubelet can restart containers to address faults and make the pod healthy again. Pods have both a specification and an actual status, with conditions that determine the pod's health. Custom readiness information can be injected into the pod's condition data. Pods are only scheduled once, and binding a pod to a specific node is called binding, while the process of selecting a node is called scheduling. If a pod fails to start on the selected node, it will not start at all. Pod scheduling readiness can delay scheduling until all scheduling gates are removed. Kubernetes may attempt to restart a failed container within a pod, but if the entire pod fails in a way that the cluster cannot recover from, it will be deleted. If a node hosting a pod fails, the pod is treated as unhealthy and eventually deleted. A pod will not survive an eviction due to lack of resources or node maintenance. Kubernetes uses controllers to manage disposable pod instances, and a new pod can be created to replace a failed one. Things like volumes associated with a pod have the same lifetime as the pod itself, meaning they are created and destroyed with the pod. In summary, Kubernetes manages pod scheduling, fault recovery, and associated lifetimes, ensuring that pods are healthy and operational within the cluster. Pod phase. A pod status field, represented by a pod status object, includes a phase field that summarizes where the pod is in its life cycle. The phase is a high-level overview and is not meant to fully capture the container or pod state. The number and meanings of pod phase values are closely controlled, and nothing should be assumed about pods based solely on their phase value. It is important not to confuse the pod status field, which may show values like crash loop back off or terminating during specific actions, with the pod's phase. The pod phase is a key part of the Kubernetes data model and API. Pods are given a default 30-second grace period to terminate gracefully, and the -force flag can be used to forcibly terminate a pod. In Kubernetes 1.27, deleted pods are transitioned to a terminal phase before being removed from the API server. If a node is lost, Kubernetes sets the phase of all pods on that node to failed. Container states. Kubernetes tracks the state of each container within a pod, which can be in one of three states: waiting, running, or terminated. The scheduler assigns a pod to a node, and the kubelet then creates containers for that pod using a container runtime. To check the state of a pod's containers, you can use the command kubectl describe pod name of pod, which shows the state of each container. A container in the waiting state is still in the process of starting up, such as pulling container images from a registry or applying secret data. Running indicates that a container is executing without issues, with any post-start hooks already executed. Terminated means that a container has either completed its task or failed, with information on the reason, exit code, start and finish time. Additionally, container lifecycle hooks can be used to trigger events at specific points in a container's lifecycle, such as pre-stop hooks running before a container enters the terminated state. How pods handle problems with containers. In Kubernetes, the restart policy defined in a pod spec determines how the system reacts to container failures within pods. The policy follows a sequence starting with an initial crash, where Kubernetes immediately attempts a restart based on the restart policy. If the container continues to crash, Kubernetes applies an exponential back-off delay to prevent system overload. This delay is reset if the container runs successfully for a certain duration. A crash loop back-off state indicates that a container is repeatedly failing and restarting in a loop. The crash loop back-off can be caused by application errors, configuration errors, resource constraints, or failing health checks. To investigate this issue, users can check logs, inspect events, review configurations, check resource limits, and debug the application code. The restart policy for a pod can be set to always, on failure, or never, with the default being always. This policy applies to app containers and init containers, but not to sidecar containers. Sidecar containers are defined within init containers and have their own container-level restart policy, which ignores the pod-level policy. The kubelet handles container restarts according to the specified policy, restarting them with an exponential back-off delay and resetting the timer after 10 minutes of successful execution. Understanding the behavior of sidecar containers and pod lifecycle is crucial for managing container failures effectively in Kubernetes. By properly configuring the restart policy at the pod and container levels, users can ensure that containers are restarted appropriately in case of failures, preventing system overload and maintaining the stability of their applications. Pod conditions. In Kubernetes, a pod has a pod status that includes an array of pod conditions that the pod has either passed or not passed through. The kubelet manages various pod conditions, including pod scheduled, pod ready to start containers, containers ready, initialized, and ready. Pod readiness can also be extended with custom conditions using readiness gates in the pod spec. These custom conditions must be evaluated for a pod to be considered ready. The kubectl patch command does not support patching object status, so applications and operators should use the patch action or a Kubernetes client library to set custom conditions for pod readiness. In addition, pod network readiness is a feature in Kubernetes v1.29 that ensures a pod is admitted by the kubelet, has required storage volumes mounted, and has networking configured. The pod ready to start containers condition is set to false if the kubelet has not yet set up a sandbox with networking for the pod. This can happen early in the pod's lifecycle or if the pod's sandbox virtual machine reboots. Once the sandbox creation and network configuration are complete, the pod ready to start containers condition is set to true, allowing the kubelet to start pulling container images and creating containers. For pods with init containers, the initialized condition is set to true after the init containers have successfully completed. For pods without init containers, the initialized condition is set to true before sandbox creation and network configuration start. The goal is for all containers in the pod to be ready, and for all readiness gates conditions to be true for the pod to be considered fully ready. Container probes. A probe is a diagnostic that periodically checks a container using one of 4 different mechanisms: exec, gRPC, HTTP GET, and TCP socket. Each probe must define exactly one of these mechanisms, with exec involving the creation of multiple processes and potentially causing overhead on the CPU usage of the node. Probes can have 3 outcomes: success, failure, or unknown, and the kubelet can react to 3 types of probes on running containers: liveness probe, readiness probe, and startup probe. A liveness probe indicates whether the container is running, and if it fails, the kubelet kills the container according to its restart policy. A readiness probe indicates whether the container is ready to respond to requests, with a failure resulting in the removal of the pod's IP address from related services. A startup probe indicates whether the application within the container has started, and if it fails, the kubelet kills the container based on its restart policy. Liveness probes should be used if a process in a container can crash on its own, while readiness probes should be used if traffic should only be directed to a pod once the probe succeeds. Startup probes are useful for containers with a long startup time, allowing for extended probing during startup. Implementing both liveness and readiness probes can help ensure that back-end services are available and that traffic is directed only to healthy pods. Using a startup probe can help differentiate between a failed application and one still loading data during startup. If a pod needs to drain requests when deleted, a readiness probe may not be necessary, as pods automatically become unready during deletion. In summary, probes are essential for monitoring and maintaining the health of containers in a Kubernetes environment. By carefully configuring and implementing liveness, readiness, and startup probes, you can ensure that your containers are running efficiently and responding to requests effectively. Termination of pods. The text explains the importance of allowing processes running in pods to gracefully terminate when they are no longer needed in a Kubernetes cluster. When a pod is requested for deletion, a grace period is recorded before forcefully shutting down the pod. The kubelet attempts graceful shutdown by sending a term signal with a grace period timeout to stop the containers in the pod. Once the grace period expires, a kill signal is sent to any remaining processes, and the pod is deleted from the API server. If the kubelet or container runtimes management service is restarted during the process, the cluster retries the termination from the start, including the original grace period. When manually deleting a pod using the kubectl tool, the pod is marked as terminating, and the kubelet begins the local shutdown process. If a pre-stop hook is defined in the pod, it will be run inside the container during the shutdown process. The kubelet manages the shutdown of containers in the pod, triggers the container runtime to send a term signal, and evaluates whether to remove the pod from endpoint slice and endpoints objects. For pods that shut down slowly, the kubelet ensures the termination when the grace period expires, triggering a forcible shutdown by sending a sigkill signal to any remaining processes. The kubelet transitions the pod into a terminal phase, failed or succeeded, and triggers the removal of the pod object from the API server. Forced deletions can be disruptive, and a specific flag, force, is required along with -grace period = 0 to perform forced deletions. When a pod includes sidecar containers, the kubelet delays sending a term signal to sidecar containers until the last main container has terminated. The sidecar containers are terminated in the reverse order they are defined in the pod spec. The text also explains garbage collection of pods, where terminated pods are cleaned up by the pod garbage collector when necessary to avoid resource leaks. Additionally, the pod GC cleans up orphan pods, unscheduled terminating pods bound to non-ready nodes, and those marked with node out of service volume detach. In conclusion, the text provides detailed insights into the graceful termination process of pods in a Kubernetes cluster, emphasizing the importance of allowing processes to shut down properly before deletion. It also covers scenarios where forced deletions may be necessary and explains how sidecar containers and pod garbage collection are managed in the Kubernetes environment.